Today we are going to learn about practical techniques for bias-variance trade-off optimization. We will explore actionable strategies to fine-tune your models by understanding and optimizing the bias-variance trade-off, ultimately improving model accuracy and robustness. Welcome to our exploration of bias-variance trade-off optimization. In predictive modeling, the bias-variance trade-off is a critical concept that affects model performance. Bias refers to errors due to overly simplistic models, while variance refers to errors from models that are too complex. Striking the right balance between these two is essential to build models that are both accurate and robust. In this video, we will delve into practical techniques to optimize this trade-off, aiming to improve both the predictive power and generalization of your models. By the end, you will be equipped with actionable strategies to enhance your modeling skills.
Understanding the bias-variance trade-off is fundamental for any data scientist or machine learning practitioner. Bias occurs when a model is too simple, failing to capture the underlying trends of the data, leading to underfitting. On the other hand, variance is when a model is too complex, capturing noise in the data as if it were a real pattern, resulting in overfitting. The art of modeling lies in finding the optimal balance between bias and variance, which can significantly affect model accuracy and reliability. In practical applications, this trade-off is not straightforward and requires careful consideration of model selection, complexity, and the nature of the data. By mastering this concept, you can improve your model's performance across various datasets. To optimize the bias-variance trade-off effectively, it's crucial to analyze model performance metrics. Common metrics include root mean square error, RMSE, mean absolute error, MAE, and R-squared, R. These metrics help us understand how well our model is performing and where improvements can be made. By interpreting these metrics, we can gauge the levels of bias and variance in our model. For instance, a high bias model might show a high RMSE, while a high variance model might have erratic performance across datasets. Evaluating model complexity is also essential, as overly complex models tend to overfit, evidenced by high variance. Regularly tracking these metrics allows us to iteratively improve our models, ensuring they perform reliably in real-world scenarios. We'll explore real-world examples to illustrate how metrics guide the optimization process. Data preprocessing is a critical step in optimizing the bias-variance trade-off. The quality of data directly influences model performance, as poor data quality can introduce bias or variance. Handling missing data, for instance, is essential to prevent bias. Imputation techniques or removing incomplete records are common approaches. Feature scaling, such as normalization or standardization, ensures that all features contribute equally to the model, reducing variance. The impact of data preprocessing on model performance cannot be overstated, as it sets the foundation for successful modeling. A case study we'll explore demonstrates how effective preprocessing transforms raw data into a robust dataset, minimizing bias and variance and ultimately leading to superior model outcomes. Regularization is a powerful technique to manage overfitting, a common issue where models perform well on training data but poorly on unseen data. Overfitting is often due to high variance. Regularization methods, such as L1, lasso, and L2, ridge, regularization, introduce penalties for larger coefficients, thus discouraging overly complex models. L1 regularization can lead to sparse models, effectively selecting features, while L2 regularization helps in reducing model complexity without eliminating features. Implementing these techniques can significantly reduce variance, leading to models that generalize better to new data. We'll examine examples where regularization has proven beneficial, showcasing its role in improving model robustness and accuracy in various contexts. Hyperparameter tuning is crucial for achieving the optimal balance between bias and variance. Hyperparameters are settings that define the model architecture and need to be set before training. Techniques like grid search and random search are used to find the best combination of hyperparameters that minimize bias and variance. Grid search involves an exhaustive search over a specified parameter grid, while random search samples combinations randomly, often being more efficient. The impact of hyperparameter tuning on model performance is profound, as it can significantly improve accuracy and generalization. We'll discuss strategies for effective tuning and provide practical examples of how hyperparameter optimization enhances model outcomes, ensuring that your models are both accurate and robust.
Cross-validation is an invaluable tool for evaluating the bias-variance trade-off. It involves partitioning the dataset into training and validation sets multiple times, ensuring that every data point is used for both training and validation. Common methods include k-fold cross-validation and leave-one-out cross-validation. Cross-validation provides insights into how well the model generalizes to new data, helping to assess bias and variance. By improving model reliability, cross-validation ensures that performance metrics are not skewed by a particular dataset split. We'll explore how cross-validation is applied in practice, illustrating its effectiveness in optimizing models and achieving a robust balance between bias and variance.
Examining case studies of successful bias-variance management provides valuable insights into practical applications. In real-world scenarios, data scientists encounter various challenges that require strategic techniques to balance bias and variance. We'll explore examples from industries such as finance, healthcare, and e-commerce, where different techniques were applied to overcome high bias or variance issues. These case studies reveal the challenges faced, the innovative solutions implemented, and the outcomes achieved, offering a comprehensive view of effective bias variance management. By learning from these examples, you'll gain a deeper understanding of how to apply similar strategies to optimize your models and achieve superior performance in your projects.
Advanced methods like ensemble learning and model stacking offer powerful solutions for optimizing the bias-variance trade-off. Ensemble learning involves combining multiple models to improve predictions, leveraging the strengths of each model to reduce both bias and variance. Model stacking is a specific ensemble strategy where different models' predictions are used as inputs to a meta-model, enhancing overall performance. These techniques can significantly improve model accuracy and robustness, as they effectively mitigate the weaknesses of individual models. We'll delve into implementations of ensemble techniques, exploring examples of successful ensemble models that have achieved impressive results by balancing bias and variance in complex predictive tasks.